Hey, this is Sammy Fodil, founder and CEO of Taubyte, and your host today for this first episode of Bourne Again Cloud. If you're wondering where the name came from, it's basically a reference to Bourne Again Shell or Bash, which is one of the most popular shell scripts in today. So today we're going to talk about um, what we call Cloud Plus Plus, or what is the next evolution of cloud from centralized clouds that live somewhere specific, like whether it's a region or a specific provider, to what we call interoperable cloud networks. So I'm gonna use a little helper here, deck on the side for those viewing the video. Um, but otherwise, I'm gonna go and talk into details of every aspect of the subject. So the major problem today with the cloud is it's a very little fraction of what's available out there as capacity. So there are roughly over 1 billion servers out there that are public facing and internet facing. Those servers are barely used, like less than 10%. We know that, like, if they were running a cloud, they could be used more because running a cloud meaning there is some kind of orchestration there, maximizing the usage of the servers. Um, and especially with edge computing and Web3, where we really need that excess capacity. We need to scale horizontally, and we also need to be decentralized, meaning not just running on one infrastructure provider. Um, that becomes very important. It's not like a strange or an alien problem to current cloud. Like, you probably are familiar with the concept of cloudflation, or the raise of um, prices in the cloud, and that's also related to that because cloud providers only use a fraction of uh, what's available out there, and they control that little fraction, meaning they control the price. And what's now the reason that, or what's the reason that, like, only roughly 1% of all that infrastructure um, is under a cloud or available through a cloud? The main reason is there is only a few players out there that have the technology to build usable clouds, or to build a cloud interface that is usable and easier to access to developers. And none of those technologies uh, they have, and they keep under wrap, like it's not accessible to anybody. Like, if you wanted to have a cloud that's usable by developers today, you either build something which is pretty complex, or you'll need some kind of partnership with one of the cloud providers, and they will deploy a product of theirs into your data center, for example. That's not an open architecture, and that's not also um, what we need today in terms of distributed computing or edge computing and peer-to-peer architectures, because it doesn't satisfy the first requirement, which is decentralization. Now, if we look at, or if we go deeper into these technologies, we'll see that they do not satisfy verifiability either. So you're running your code out there, but you don't know if the code was run correctly, if your code was modified or altered in any way at all. Uh, and then the last point there is even if you, let's say, you deploy like multiple regions with a hyperscaler, or use a product, let's say Kubernetes or any one of those existing cloud products, you'll find yourself that you're not satisfying verifiability for sure, but also you have no autonomy. So you have to do a lot of DevOps and a lot of automation, kind of like people making sure that it's scaling all the time. Um, and that's not very effective when we're talking about like planet scale software, really. Most of all, and that goes back to that autonomy and automation. When the developer, which is the real user of the cloud, tries to get there and use a cloud, they're faced with operators, administrators, and so on. So before accessing any kind of cloud, they need to do some kind of extra work or need some extra help, like a DevOps team, for example. So, and this is why we think at Taubyte that, and you probably heard of platform engineering, right? Like platform engineering is that new way of trying to abstract the DevOps team and offer developers like some kind of usable infrastructure. That's a good step forward, but I think we can just skip that and go to autonomous infrastructure. And this is really what we believe Cloud Plus Plus is a Taubyte, and this is what we focus into building. So basically, we build that cloud uh, platform or open source cloud platform that presents a cloud native interface on the front. So you have mainly focused on serverless today and WebAssembly, but we'll be bringing in containers and VMs down the road. But the interface is really all cloud native. Like you develop on Taubyte, it's cloud native. Under the hood, it's a peer-to-peer network operated by protocols or peer-to-peer protocols instead of APIs. It's also uh, based on GitOps. So, like, there is nothing that you cannot change the network without changing your definitions uh, in GitHub. And this is also part of what we think a Cloud Plus Plus should be. Like you shouldn't be able to modify anything without modifying the definitions, let's say in a Git repo. Okay, so how do we achieve some of those requirements? The first requirements that we talk about was decentralization. So that decentralization can be satisfied by enabling cloud ownership uh, and or diversity, right? So it's either you can deploy your own cloud in easy way and have your developers use that cloud platform, or there is so much diversity of clouds, like hundreds of thousands of clouds, if not more. You have like the choice of choosing from all of these clouds, and because they're using protocols instead of APIs, they're interoperable from the get-go. Verifiability can be ensured using cryptography, right? So the Taubyte, we use the concept of content addressing, which has been around for a long time. It's been used by peer-to-peer networks like BitTorrent, and then in the Web3 space, IPFS uses content addressing. So basically, instead of saying this image or this file is on this specific server and this specific path, we say like this is the hash of the file, and the hash is basically like a number or a big number that represent the content of a file. If the file changes even by a little bit, that number changes. So that allows us to grab resources in a verifiable way. So now I have my resource available in the network. It's not in a specific place. I can discover it. I can ask other peers for it and basically grab it faster. But once I grab it, I can verify, I can rehash it and validate that the content is authentic and didn't change. The other aspect is encryption. So in the peer-to-peer network that Taubyte is built on top, every node has its own identity. So uh, you cannot pretend to be another node. You cannot send messages in the place of another node. So we have a validation and verification from that standpoint. The last point that we also use is zero knowledge proofs, and we use that in different ways. One way that we use is through a protocol that we call um, a proof of integrity. So, and that takes us a little bit to explaining what types of computing is out there. So, computing can be divided in two parts: deterministic computing and non deterministic computing. So, deterministic computing is when you run a computation that always gives you the same output given the same input. That's the case of a mathematical function. It's also the case of a smart contract, right? So, for a smart contract or a mathematical function, you can generate what's called a ZK circuit. And the ZK circuit can be used by the prover or proofer to generate a proof, and by the verifier to verify that the proof is correct, right? And this is how ZK is used in L2 networks, for example, to accelerate transactions. So not so the nodes do not have to run the smart contracts again and again to verify the output. So that set apart, there is that bigger chunk which represent most of the compute or the computing today and tomorrow, which is non-deterministic. And the way we can solve that is by minimizing trust. So we cannot really verify the output because there could be random numbers there. There could be a network request that failed and was retried and given different values and so on, right? So the way we do that is by verifying the integrity of the nodes. And we do that through a protocol. So when a node joins the network doesn't trust it. And then it's like, okay, what do you want us to trust you for? And the node will say, hey, trust me for, let's say, storage. And this is something that's common. And it will like the node or some of the nodes say, okay, give us proof of storage, give us proof that you stored the data, give us proof that you have space available, right? And those are used by networks like Filecoin, right? But in the case of Taubyte, it's more like flexible proof. Like when a node joins the network, because it's part of a cloud, it can offer storage, but it can also offer computing, or it can offer messaging, or any other cloud native resources. So the way it works is it's basically an exchange, right? So the node joins the network, it it pings another node. Let's say just a pick one. It's actually it could be more than one. It says like, okay, can you trust me? I'm joining the network. Can you trust me that I can provide WebAssembly computing? Just for an example, right? Um, so the other node will say, yeah, let's see that. Here's a challenge. So he's gonna send a challenge to that other node, and that other node will have to solve the challenge and provide a ZK proof that he knows the response or the answer to the challenge. So that ZK proof will also include the signature of the challenger, and would be, if that ZK proof is valid, can be used by the node asking to be validated and trusted, and presented to other nodes in the network. So other nodes can say, oh yeah, this node has a verified proof. It's valid. It's signed by that other node that we also trust. You're good to go. And this is how that part works. Um, now let's move to the next thing, autonomy. Right, let's move away from that centralized cloud that runs on a one data center with a very predictable cluster. We're more talking about like a mesh network and uh, infrastructure that is distributed horizontally across servers and Raspberry Pis and cores and different types of devices. And we're like, okay, how do we ensure that the software will run where it needs to be? How do we ensure in the case of, let's say, share the resources, let's say a 5G cell tower with some computing in there, that the resources are shared, right? And we do that um, through consensus, different consensus protocols, through the discoverability and what we call just-in-time ops or smart ops. I also refer to them as serverless ops, not ops for serverless, but rather serverless ops. And we'll get to why I call them that way. So for consensus, there are two big types of consensus that we use. We use CRDT, and CRDT is basically conflict-free replicated data types. The strength of CRDTs is, even if there is a disconnection that happens, the data will converge into a consistent state when connectivity comes back. A good example for that in the 5G space is a car um, that is 5G enabled and moving from one cell tower to the other. So once the car, like in the like the way it's like people are trying to do it today is try to predict where the car is going, right? That's quite heavy. The right way we think it should be done is using CRDT. So the car is going to move to the next tower, and that next tower is going to spin up, let's say, a storage or a database. But because the database is CRDT, it's going to accept the writes, like writing data into it and from the car. But in the backend or under the hood, the database is going to synchronize with the previous tower, right? And synchronize the data in a conflict-free way. When it comes to data that cannot converge and needs to be agreed upon all the time, let's say a financial transaction, right? Or where you need to specifically provision a non redundant resource, let's say a regular MySQL database, right? In that case, we need a stronger mechanism, and that's BFT, right? Let's say Tendermint, which Ethereum uses, and that's also what we use. So basically, nodes in the network will agree on who's going to run the resource, and then the resource is going to run only in one place. The second thing is discoverability. So, how can you discover where things are in a distributed network? Well, we use a concept that's not new. It's been used before, and it's used by peer-to-peer networks, including IPFS, and that's a distributed hash table. So remember, like every resource has a hash, and this is how we find it. It's not using like an IP address and a port and a path to it, like what we do in, let's say, Web 2 or regular web. The way we do it is like we'll look for a hash. So if I'm looking for a file, I'm looking for the hash of the file. Because the distributed hash table is really a circular table, we can look in that table which node is closest to that hash, because the nodes IDs are also hashes. And then we can determine which node should have that. If not, we can just broadcast to nodes we know, say like, hey, do you have that? That goes and is valid also for services. So if I'm looking for a protocol or a node that provides a protocol, let's say slash Patrick slash V1, which is like part of the CI/CD protocols that we use at Taubyte. Um, uh, the node is going to hash that and then say like, hey, where is it in the hash table or the distributed hash table, and find peers that should be provided that. And then the last one is what I quoted, like smart ops or just in time ops, or again, like also like serverless provisioning of resources. So instead of defining or declaring what needs to be provisioned ahead of time, which is how you would do it with Terraform or Kubernetes or any other um, uh, cloud, not cloud plus plus technology, we do it differently. So we use smart ops, which are basically WebAssembly functions that have host or they have SDK that can talk and alter or query infrastructure, right? So basically, let's say before you provision a function, you need to see if a specific 5G slice is there. Or before you store data, you need to make sure that the user and the node are in the same locality because of GDPR and so on, right? So all of these can be done just in time with smart ops that optimizes for resources, um, but also makes the network autonomous. And then the last one is like all of this is amazing, but if the if developers don't like it, like what's the point, right? If you look at Kubernetes, it's very hard to use, very hard to scale, and that's the case of every product out there because it was made for operators. It wasn't made for developers, and this is where we decided to be different. Like we need to create amazing tools. We need to create this platform for developers. We need to use convention over config because like who likes a lot of config, right? Like a lot of things can be made into conventions. For example, in Golang, which is the programming languages that we use mainly at Taubyte too, like to export a function, you just need to have the first letter being uppercase, right? That's it. Like, and we use conventions all around to simplify config, to simplify things. Already talked about no ops, so unless you want to add some of that smart ops in there, the platform will just optimize for resources and look for being provision functions and resource closer to the user and so on. So talk that everything is on Git. So that makes total sense to developers. That's what they use all day long. And the last thing is we have a built-in CI/CD using two protocols, Patrick and Monkey, and basically they will grab your code, build it, verify the build, and push that to the network. So just to recap, how does it compare to other open source products besides VMware there in that list? Like I said, Taubyte is like or Cloud Plus Plus too. Like it shouldn't be DevOps oriented, right? Like Cloud Plus Plus should be for developers. Let's drop all of that complexity that we add to the cloud that requires like people to do operations. Let's drop that deployment complexity by having like this autonomous cloud that can discover resources. Uh, and then we really need to scale horizontally in edge computing and Web3. So dropping or focusing on how we scale horizontally using or leveraging those new techniques from the DHT, direct, direct, direct acyclic graphs, and other concepts like CRDTs versus like just relying on those centralized approaches like master and slave, client and server, sharding, and so on. Verifiability is an important part, especially at the edge, whether it's for Web3, because like in Web3 you need to verify everything, but also for the edge, because edge servers and nodes are easy to hack into. We need to make sure everything is verifiable, optimizing for resources with just-in-time ops, and that's mainly like what we think Web3 should be all about, and and that's about it. I think um, we we've gone through uh, a lot of concepts here. I know a lot of them are new to most people, um, and what I want to say is, uh, hopefully this episode brought some new concepts that you cannot think like, okay, maybe it makes sense. Like it makes sense for me, it makes sense for us, but I want you to verify, right? Really verify that it makes sense. And one way to do it is um, look at our code in GitHub. Go to console.taubyte.com and build something on our sandbox. And soon enough, like in about a week or so, we'll have tools so you can also easily deploy your own Taubyte cloud and test all of that yourself. Uh, Thank you for attending this first episode, um, and I'll see you in the next one. Thanks.